So one of the culminating problems in the class, especially in the strain transformation, is dealing with problems where there's a single strain gauge, but it's off of a major axis. There's some rotation to it. So it's not sort of on the longitudinal, the hoop direction. Right? It's at some angle. So here's a problem where this gauge is sitting at a known angle of 18 degrees. And what we're going to do is, if you kind of read through it, we're going to determine the pressure in the tank, knowing that the strain gauge has some reading. And so what we'll end up doing is, in these problems relating stress to strain, and then we're going to take an initial strain state and we're going to rotate it to the gauge. So think of conceptually, we need to go get to the gauge. We need to go take our strain state and rotate it such that it aligns with the gauge which has a known value on it. So again, I'll let that sink in here just for a second. We've got a gauge, right, that's sitting up here at some angle. So what we want to do is we want to analyze some initial state, and we'll end up doing stress. We'll then use 3D Hooke's law to get it to strain. And then we want to take that, and then instead we want to put it on the angle of the strain gauge. And so then the reading on the gauge is going to give us the answer on the x prime axis. So we use the fact that we know quite a bit about a pressure vessel. We've got a cylindrical pressure vessel here. And so we would know that the initial state of stress is going to involve the hoop stress and the longitudinal stress, which are related to each other. So we'll keep the solution symbolic until the very end, and then we'll plug in numbers. But we do know that the hoop stress is going to be PR over T, where R is the mean value, and the thickness is going to be 6 millimeters. And we've also got some values for the material. We've got an E right here, and also Poisson's ratio. Right, we'll need to keep into account, right, the units police as we get ready to do some Hooke's law. So the hoop strain, right, we can calculate the hoop strain from the initial stress. And so we're just going to use 3D Hooke's law, where we take the stress in the hoop direction divided by E minus Poisson's ratio perpendicular. So we've got sigma longitudinal divided by E. We're on a free surface, so the radial direction is equal to 0, right? Also thought of as the Z direction. So just plug in what we know there, and we now have an answer for the hoop strain. And I'm going to use sigma H as shorthand for the hoop direction right there. All right, there's E. I'm just going to carry it along with me, and numerically we end up with 0.85 because we end up with 1 minus Poisson's ratio divided by 2. So we're going to do the same thing for the longitudinal strain. This will give us the initial state of strain. And so we just plug in those values, and we end up with 0.2. And so we've got two strains that are both positive from this. And so let's just go ahead and approach Moore's circle for strain. Right? And again, the reason why I want to do on a Moore's circle for strain is because we know the normal strain at 18 degrees, right? At 18 degrees on that strain gauge right there. So let's go back and look at our, just drawing on the strain. So there's our initial state of strain, the hoop direction, the longitudinal direction. And as those are just calculated above here, so all I've done is kept those on. I'm going to keep sigma hoop divided by E and go to Moore's circle for strain. On the horizontal axis, I'm going to use units of sigma H over E, so that just gives me 0.85, 0.2 plotted. Gamma over 2, there is no initial shear strain, right, because of the pressure vessel. So we can calculate the center of the circle, right? Just take the two normal strains, divide by 2. So we got 0.525. We can find the radius of this, which is just going to be the diameter of it, divided by 2. So I'm going to take that entire length. So to do that, I'm just going to subtract those two numbers and divide by 2. So there's the radius is going to be 0.325 times sigma h over E. So really the next move that we do is, quite honestly, the most important move that we've got to do here. And what we want to do is take the initial strain state, which is sitting right there, and we need to align it with the gauge. So the strain gauge is sitting at this orientation at an angle of 18 degrees. So I want to take this strain state picture and I want to find its answer, at 18 degrees. And then, keeping close track of our axes, there would be x prime, y prime, rotating our axes. And so that would mean that the answer on the x prime face would have to be the plus 280 microns. So on the circle, 18 degrees in real life is going to end up at 36 degrees. So there's going to be x prime. There now is the y prime. And so this is going to be at 36 degrees right there. And I know that if we drop that down, right, that number right there is going to be the reading on the gauge. It's going to be the normal strain on the x prime axis. So that number right there is going to be plus 280 microns. So that's really the money setup. And now here's the money shot, is how do we get an equation that uses 280? And it's just sitting right here on the page for us. We just have to be observant. So to get to 280, we need to go to the center of the circle, which is 0.525 sigma h over E. And I'm going to add to it the radius of the circle times cosine, 36 degrees. Right, there's our angle, 36 degrees. So the cosine of 36 would be the radius times cosine 36. It would be that distance right here. So that gets us all the way to the strain gauge. 280 is going to be calculated from the center plus our cosine, 36 degrees. And once we've got that set up, that'll give us the ability to now solve for the hoop strain, or hoop stress, excuse me. We'll be able to use this equation to solve for that unknown. And then we just keep working backwards all the way to the pressure in the tank. So it just becomes math from here. We use a little bit of units police, get ourselves home. There's our equation for sigma h has been brought out. Solving for it using also units police here. Right, we've got gigapascals, which is 200 times 10 to the 3 megapascals. And generally, that'll be in units of megapascals. We relate then the hoop stress back to PR over T. Using the values, we then find the pressure in the tank. So big summary point is we want to go get the gauge. We need to go to where the gauge is, where the strain gauge is. And we know the reading on the strain gauge, and we can relate that back to the parameters on Moore's circle for strain. All right, I'll also go through the solution by the strain gauge equation. So off your equation sheet, we've gone over this equation a few times. And so we can go ahead and solve this thing by using this equation. So I'll do it for you. The approach that you want to use, again, is up to you. The initial strain state, right, would need to be calculated. So that would be exactly the same as above. So everything we did above about stress to strain and 3D Hooke's law would be applicable. For the gauge, epsilon I is equal to 280. The angle theta I, right, would be measured from the x-axis, so it's going to be plus 18 degrees. Right, there's our values. Gamma, the initial shear strain, is equal to 0. So we're going to plug all those in, and we end up quickly back at the exact same spot. A little bit different, but the math will come out the same, and we've got a sigma h equation. Some of the numbers obviously look different, but there we end up with the exact same answer for the hoop stress. So all we've done is used the strain gauge equation, and we've just used the fact that we had solved for initial strains in terms of initial stresses. We knew that one was equal to 0. Right? We know that value right there, that's given to us. We also know thetas, and we're able then to create our one equation, one unknown, because both normal strains relate back to the hoop stress.